All right, I think it's 4:30, so we can get started. So it's the second talk in the afternoon. So the speaker is from National Taiwan University, Professor Zheng, and the title is Normal Metric Concentration, Inequality, and Error Exponents for Quantum Soft Cover. Let's welcome.
Okay, thanks, Professor Huang, for inviting me here. And today I will talk about this matrix concentration and quantum soft covering problem. So this is not a very mathematics talk because our motivation is from quantum information theory. We want to solve a problem called error exponent for quantum soft covering. And in the end, we find that we'll use some mathematical tools to solve this problem. And this is closely related to matrix concentration. Okay, and this work is jointly collaborated with my good friend, Legendre at the Department of Mathematics at University of Houston. And our work can be found on archive here. Okay, so let me start. So what is concentration inequalities? It's a very useful tools in many theoretical engineering problems and probably in some applied mathematics. So let me give you some examples. You probably already know there are some Markov inequalities. If x is a random variable, then the probability of the event that x is deviate from is larger than some epsilon constant is upper bounded by this exponential minus, we call this the rate function epsilon, which is defined by this. This quantity is actually can be viewed as the Legendre transform or convex conjugate function of the this x. Okay, so you probably already know this in your probability course. And when you take this x random variable in an IID way, then we can bound the deviation of the average from its mean by some constant. Then it will decays exponentially fast. And there are some constant here, m appear in the right-hand side, and provided that the random variables is bounded almost surely. So that's what we call the Hoeffding bound. So it's a kind of concentration inequality for the IID case. And there are other variations of concentration inequalities. For example, Kramer and Chernoff, they show in a large deviation theory that the probability of this we call it average or the empirical mean deviate from, if we consider zero mean random variables, then it means that the probability of the empirical average deviates from its ensemble average, which is zero, by some constant epsilon, will exponentially decay as this, and this I is also the rate function. Okay, and in the end, in strong large deviation theory, it was shown that this rate function is actually optimal, and also they can determine the optimal prefactor in front of the exponential. They obtain this big theta notation for this probability deviation. So they are all known concentration inequality results, and you can find all of those concentration inequalities in this book written by some French mathematicians. And this book is actually very useful in machine learning, in high-dimensional statistics, and so on. Okay, so if you are interested in, please check this book. But now we are not talking about the classical concentration inequalities. We are moving from the classical random variables to random matrices. So let's look at the matrix concentration inequality and what does that mean. So we let x1, x2 to be independent random matrices on D by D random matrices, and they can take complex values. And there are similar versions as the classical concentration inequalities. We call it matrix Bernstein inequalities. So let's make some assumptions. If this random matrix deviates from its mean and the largest eigenvalue is upper bounded by L, and we can if we can bound some variance quantities, then we can calculate this z, this random matrix z, because it depends on OXM, so this z is also random. Then matrix Bernstein inequality says that we can calculate the expected operator norm between its random matrix from its mean by by some numbers depending on the size for averaging, the size control, the operator norm, and so on. And you can also use this expected operator norm to bound to get a probability deviation bound. Okay, so you can find those matrix concentration inequalities in this book, Introduction to Matrix Concentration Inequalities, written by Joe Trapp, a professor at Caltech. So there are many similar developments as in the classical concentration inequalities, just shown here. So it's a fundamental question. Can we obtain a tight matrix concentration inequality, but for the trace norm, not for the operator norm? Here, this operator norm is just the largest eigenvalue if we consider the finite random matrices. And why do we want to consider this trace norm? Is because our motivation is from quantum information theory, and we usually use the trace norm to bound the distance between two density operators. So we are concerning trace norm. So we want to ask, does any matrix concentration inequality hold for trace norm? Of course, you can translate the operator norm back to the trace norm, but you will lose some dimension factor, this D here. But we don't like that. Yes.
In what sense do these two inequalities hold?
In what sense? Oh, but here there's no randomness because you take expectation and probability. So it's like just like the classical concentration inequalities. Either you care about the deviation bound or the expected deviation.
Can you rule the expectation or the operation of probability?
Okay, so in theoretical computer science field, we can say if set this right hand side to be some delta, then you just say that this event holds with high probability, blah blah blah, something like that. Yeah, but they all come from this probability deviation bound. Okay, then I'll explain why do we care about this trace norm. Let me give you an example. We care about these trace class operators. So if you consider a classical quantum channel, which is a map from some alphabet, we call it a classical set, to a set of density operators, which are positive semi-definite operator with unit trace. We call that they are density operators. We call this a classical quantum channel. So assuming that this machine is like a classical quantum channel, and you have some coins, random coins, and you throw in, you will get some quantum state as the output. If your input is random, then of course your output will be random as well. So the randomness, the output space also have some randomness. So if you care about the output space, then you will have a bunch of random states depends on your randomness coming from the input. So what I want to say is that the classical randomness from the input will be translated to the output space. So we are concerning the concentration phenomena at the output space. So that's our motivation. Okay, so that's the short introduction. Let me jump into the problem formulation. Okay, so let's fix a classical quantum channel. We use this notation n, from, which makes some classical symbol x in some alphabet, capital X. And the output, we use this notation, rho bx, meaning that this rho bx is a density operator on some Hilbert space HB, and their densities. But this output depends on the input symbol x. Okay. In the classical case, what I mean by classical case is that the output is just a conditional probability distribution. Given each x, then the output is a measure on some probability space y. Okay, so that's the classical case, and we call this a quantum case because the output is density operators. Okay, so given an input distribution px on the input alphabet x, the output can be written as this rho b. It just you take the expectation over this rho bx. Why is that? Because for each x, we will have density operator rho bx, and if each x is distributed according to this probability distribution, then the output will be, because this is a linear map, so at the output we will have this the averaging of the density operators. We call this rho b. Okay, so here's the question. Suppose that you can sample from the input. You can sample from this x. You can random draw this x according to some probability distribution, and you can query to the channel. Meaning that whenever you have an x, you can throw in the channel, and you can get a density operator as the output. How can you approximate this ideal rho b, the averaging, the true averaging, by querying to a channel? How can you do that? So that's the first question. And naively, we can use some random codebook. I use this terminology in information theory. It means that we draw m samples, x1, x2 to the x capital M uniformly, equiprobably, when small m is in 1, 2 to the capital M. And then for each x, they are pairwise independent, drawn according to this px, the probability distribution. So we take samples. And for each xm, we query the channel to get a channel output corresponding to the symbol, input symbols. And then we mixture them because now we have m samples. We will just mixture them, meaning that we sample them equiprobably. So meaning that we draw some small m randomly, uniformly, and use this codebook, and this codebook is random, so each one is random. And then for each symbol we send to the channel, we can get a output. We call this rho b c. If this c is like a realization, then the output will be the mixture of density operators when O of x in the codebook. Of course, this c is random because now we are conditioned on this c, and in the end we need to take expectation on this c. So we call this the codebook-induced output density because it depends on the codebook, the realization of a bunch of samples you got. Okay, so now the question is, for each capital M, the number of samples we made at the input, then how close is rho b c to the desired marginal rho b? And here this c is random, so we can derive the probability deviations or the expectation of the deviation. Okay, so talking about the deviation, how do we measure the closeness between these two operators? We use the trace distance, the trace norm between these two density operators, and we put a normalization constant 1/2 here. And this trace norm is defined by the Shelton 1 norm. You take the absolute operator and take in a trace. I want to mention that this error criterion reduced to the classical total valuation distance between two probability measures in the classical case. In the classical case, I mean everything commute, every density operator, they share the same eigenbasis. So this trace distance equal to the total valuation distance in the classical case. Okay, so then now we have this question. For each codebook size, capital M, how small or how large is this expected trace distance? We are concerning the expected deviation of the codebook-induced density from the true density. You can view this as an ensemble averaging, and you can view this rho b c as an empirical averaging. Okay, and we often call this one-shot quantum solve covering because we don't impose any specific structures on the channel. We'll use that later, but if you take this question, we are actually asking a question about in a one-shot setting. I mean, there's no IID structure. Okay, so let's move on the non-IID case. We call the memoryless asymptotic setting. What does that mean? Now we consider the product channel. We call it product channel, tensor product channel, or memoryless channel, which maps any sequence xn. Xn is just x1, x2 to the xn, a sequence of symbols, and you map these symbols to a bunch to a big density operators, which is a tensor product from the first one, tensor the second one to the last one. So we call that the product channel. Every channel is tensor product. Okay, and in this case, we just consider the IID input to IID input. So this n sequence is distributed from this px tensor n, And then you will get a true marginal density by just putting this px tensor n through a channel, and by the linearity of the tensor product, you can get the true output is rho b tensor n. Okay, so that's the true marginal, but we want to approximate this density operator. So how do we do? And we use this, we call it IID random codebook. We use these probability distributions to sample. Each time we'll sample from a sequence, and then we query the channel, we get an output. So it's just like before, we take like capital M samples, and then we query some codebook, and then we send to the channel, and we get this codebook-induced density or codebook-induced state as this, which depends on this Cn. Cn is a realization of the codebook. And in this case, because we are using n ID channel, we will often set this capital M to be exponential nr. We use this capital R to describe the rate of the growth of this codebook, the codebook size, the rate of the codebook size. M equal to exponential nr. You can take this exponential as just 2. Then it means that this capital M has nr bits. We have nr bits, that many cohorts in the codebook. Okay, so now in this memories asymptotic setting, we are asking how fast does this n short, because everything depends on small n short codebook-induced density converge to the true marginal density rho b tensor n in the number of channel use. So that's our ultimate question. Okay, so is everything clear at this point about the problem formulation? Yes?
Yeah. Why do you study this quantity instead of just like a standard deviation of the distribution?
Because right now we are caring about the output. We want to approximate the tensor product, and we want to sample some input and query the channel and use them and mixture them. You can view this as an empirical averaging.
Seems like you are describing a variance of the empirical output
with the ensemble mean. Yes, exactly. So it's a deviation from the empirical averaging from the ensemble averaging, but now they are all density operators. Yeah, and we use the trace distance to measure how close they are. Okay, so actually this problem was studied in the classical case. In the classical case, everyone considered just the probability measures, conditional probability measures. So it actually studied back in the information theory community in 1975. They call it soft covering. So I use the same name. Why they use this soft is because it's in probabilistic flavors. They calculate the expected deviation or the probability deviation bound. So it's not the exact approximation because they are random, right? So it's in probability sense. So they call this soft covering, and there are some reasons why they want to study this problem. Okay, and okay, but you can also de-randomize it. If you can control the expected deviation, then you can ask how to de-randomize it to find the optimal sequence, optimal codebook to achieve this deviation. So they call this channel resolvability problem. And in the end, people find that in the classical case, people find that when this rate of the codebook is strictly larger than the mutual information between the input, because at the channel input you have some probability distribution, and at the channel output you also have some conditional probability distributions and calculate the mutual information. If this rate is strictly larger than its mutual information, then the expected total variation distance will vanish asymptotically. On the other hand, if this rate of the codebook is too small, then let's show that the expected total variation distance is bounded away from 0. You cannot achieve a perfect approximation. Okay, And here, the mutual information is defined by the Kullback-Leibler divergence in the classical case between the joint distribution and the product of the marginals. Okay, and there are many applications of these results, so that's why information theorists study this problem. There are many, but I will go to the applications later in this talk. Okay, and people also study the one-shot setting. There's no tensor product, and Masahito Hayashi, he's an information theorist. He first established exponential convergence when the rate is large enough than the mutual information in a classical case. And also, many people also study this, what's the best exponential convergence in this case. And then at 2019, people obtained the optimal error exponent to describe this convergence phenomena. Okay, and there are also many, in this talk we use the trace distance, but there are other people use relative entropy or other Rényi divergences and Washington distance, different measures to study the convergence. Okay, I will just skip that. Okay, let me jump into the literature review of quantum setting. Also, there are some quantum people study this question, and probability deviation bound was proven by Aswit and Winter. Aswit was a mathematician in Germany, and he also got the Shannon Award. Let's show that we call this a codebook-induced state, or you can view this as empirical averaging. The probability deviation of this empirical averaging from a true ensemble averaging can be bounded as in this way. They call this the operator Chernoff bound. Here, this inequality is in the sense of partial ordering, in the matrix ordering, in positive semi-definite orders. So you can view this as operator norm inequality, operator norm, because it's an operator order. Okay, and later Masahito Hayashi in his books also derived some bounds, but the first one in the quantum case was studied by this. Okay, but this does not answer my question, because this essentially this is in the operator norm, it's not in the trace norm. So, but you can translate the operator norm to trace norm, but again you will lose some dimension factor in the end. Okay, so that's some historical remarks. And why do I care about the trace distance is because some people, Holevo and Hailstrom, they study the quantum state discrimination problem. What's the quantum discrimination problem? They show that if our system is described by 0 or 1, in 0 it means that the system is modeled by some density operator, rho 0. If the system is 1, our system is rho 1. And we want to perform some quantum measurement to distinguish the system is in the state rho 0 or rho 1. So that's called a quantum state discrimination. So, and Holevo and Hailstrom, they show that the best, the optimal error probability, because if you decide 0 but the actual system is in 1, then you made a mistake. So you can calculate the error probability in this setting by optimize all possible quantum measurements. Then they show that the minimum error probability is given by this 1/2 minus the trace distance between rho 0 and rho 1. So it means that the error probability is governed by the trace distance, meaning that we want to, if this trace distance is very, very, very small, then it's not possible to distinguish those two states, because if this trace distance is 0, then you just a random guess which is the true state. Okay, so it means that we would like the empirical average to be physically indistinguishable by any possible quantum measurement to this rho b. Then we have to use this trace distance because of the Holevo-Hailstrom theorem already guarantee that. So that's the reason why we want to use this trace distance as an error criterion. Okay, as I mentioned before, you can also use other distance measures to bound, but if you want to translate back to the trace distance, then you might lose something by this in the translation of different distance measures. So in this work, we directly calculate the expected trace distance in this quantum self-covering setting. Okay, let's first go into our result, and I'll show you the proof later. So to show our result, let me introduce some quantum information entropy quantities. Let me introduce the two quantum Rényi divergence. Okay, the first one we call it sandwich Rényi divergence between two density operators rho sigma, and we call it the alpha star, defined by this. It's kind of a bit ugly, but we can write this quantity in terms of an shortened alpha norm. Shortened alpha norm is just the usual norm for Hermitian matrices. Okay, so this Rényi divergence is defined by some alpha norm, and also we define some pet Rényi divergence, the alpha, by probably more simpler formula. But these two divergence will recover the classical Rényi divergence if rho and sigma commute. If they share the same eigenbasis, then these two quantities are actually the same. But in a non-commutative case, meaning that rho and sigma do not share the same eigenbasis, they are different quantities, and they are both have operational meanings. Okay, so they are divergence to measure the closeness of rho and sigma. When alpha goes to 1, both quantities converge to the usual quantum relative entropy. And I'll just write here. The usual quantum relative entropy is defined by rho log rho minus log rho sigma. And this is positive semi-definite, meaning that this quantity is 0 if and only if rho equal to sigma. And those two quantities, they all satisfy this positive definiteness. So that's why we like to use those divergences. Okay, then we will further introduce some information quantities. Given an input distribution at a channel input, Px, a classical distribution, and a classical quantum channel, we can introduce a joint state between channel input and output just by this formula. It's a joint distribution. You can view as this way: a joint distribution between input and channel input and output. But in this case, the output is a bunch of density operators. The output is quantum. Okay, and then we introduce this sandwich Rényi information. We just it's a sandwich Rényi divergence between the joint distribution against the product of the marginals. But here we optimize over the second argument, sigma b. We use this sandwich Rényi information. And then we also use another information quantity we call a pet Rényi divergence, which is just the pet Rényi divergence between the joint state between channel input and output against the product of the marginals. Here we put the marginal here. Those quantities, they all converge to the usual quantum mutual information. Quantum mutual information, I put 1 here when alpha goes to 1, and it's defined by the quantum relative entropy, this guy, and to calculate the divergence between the joint distribution against the product of the marginal. Okay, so they have both have meanings. Okay, so with those information quantities, now we are ready to state our main result. The first result we call the one-shot error exponent is given by the following. For each input distribution Px, every classical quantum channel, we have this joint quantum state between channel input and output. Then our first theorem is that the expected trace distance between the codebook-induced density from the true marginal density is upper bounded, is controlled by this exponential decay of this form. Exponential of E star, we call this the error exponent, defined by this form. You may think that this is kind of ugly, but actually it has the same form as a convex conjugate, or the Legendre transform you saw at the beginning of this talk. Up to some parameterization, for the usual information rate function that I introduced at the first slide is something like t times epsilon minus the log the moment generating function, something like that. So up to some parameterization, this exactly has the same form of this differential Legendre transform. Okay, so that's our first result. We call this the sandwich error exponent. Okay, and I want to remark that this error exponent is positive, is strictly positive if and only if log m. What is log m? M is the samples you made, or the codebook size. And log m is just the number of bits of the codebook. If the number of bits of the codebook is strictly larger than the mutual information, rho xb I just written here, then the error exponent will be strictly larger than 0. It means that this will be meaningful. If and only if the number of bits of the codebook is larger than the mutual information. So that's the interpretation of this theorem. Okay, and I want to mention that this I alpha star, there's no closed form expression in a non-commutative case. In the commuting case, in the classical case, it has a closed form expression, but in the quantum case, it's an optimization. But we have some paper to propose some optimization iterative algorithm with convergence guarantee to calculate this quantity. So it's also computable if you put in your Python or MATLAB or Mathematicas, you can calculate this quantity. So we can answer this question by obtaining this analytical form of the error exponent. Okay, and we also get some lower bound. We call it one-shot strong converse bound. Again, for each input distribution, CQ channel, for this joint state, we obtain this lower bound. We lower bound this expected trace distance by 1 minus some exponential decay form. This E down arrow is defined by the Rényi divergence. It has the very same form with some different parameters. And this, we call this the strong converse exponent, is positive if and only if the number of bits you used to sample is strictly smaller than the mutual information. So it means that if the samples, if the codebook size is too small, then this strong converse exponent is positive. It means that your expected trace distance will be bounded away from 0 and probably approaching 1. So that's our result. Okay, let's go to the IID setting where the input distribution is IID tensor product of the probability distributions, and we can have the induced joint density operators between channel input and output, and just a tensor product of rho xb. In this case, by just using the additivity of the sandwich Rényi information proven by some people, and also by the additivity of the Rényi divergence, we immediately get this result. The expected trace distance between the codebook IID codebook-induced state and the true rho B tensor n exponentially decays in the number of n. This n is the number of channels we used. And this exponent is given by, we get this upper bound, and we get this upper bound and the exponent by this the sandwich error exponent. And as I mentioned before, this error exponent is positive if and only if this rate is the number of bits per channel used, so we divide this quantity by n, is strictly larger than the mutual information. On the other hand, if the rate is too small, then this quantity will approaching 1 exponentially fast because this quantity will be strictly positive if only if the rate is too small. So that's our immediate result. Okay, and I want to mention that both result holds for any Bloch length n. It's not just holds asymptotically, it holds for any finite n. It also means that this mutual information is like a fundamental limit to decide if you can approximate the rho B tensor n well or not. It can be approaching 0 exponentially fast, or it can approaching 1 exponentially fast. Let me use this picture to illustrate. Let's suppose that this rho B has full support. Its full rank rho B tensor n is like this. And you can randomly draw a sample to get some sequence at the input xn according to some ID distribution. And you curry the channel, you can get some rho B xn, like some density operator at the output like this form. This rho B, this guy, the purple guy, might not be the same as rho B tensor n. And also, this guy might not have full support. It could be just the rank can be just a few low rank densities. Okay, and the eigenbasis of this purple guy might not be commuting with rho b tensor n. But if you draw several times, you increase your code book and you draw several times, and you mixture them, then the mixture of those purple density operators will approach rho b tensor n strongly, because we now consider the trace distance. So it's not in the convergence is not weak in the weak topology, it's in strong topology. And also the convergence is exponentially fast in the number of n. If you use channel many times, and then the number of code book size m, we define this m is exponential to the nr. So if this n increase, then this convergence is exponentially fast, and we give an error exponent for this convergence. So that's the meaning of our result. On the other hand, if this m is this r rate, the rate of r is too small, then you can never achieve a good covering of the ensemble averaging. Okay, so that's the meaning of our result. Okay, let me give you some remarks. We want to make some comparisons to the classical results. First, our one-shot achievability, meaning that the one-shot error exponent bounds recover the one-shot bound by some classical information theorist in 2020 in a commuting case. So we directly cover some classical result. And also, yeah. But we use totally different proof techniques. The technique we proved these results by the norm interpolation. I will describe that later. And we expect that the error exponent obtained is asymptotically tight, meaning that we already obtained the best error exponent, meaning that we expect that this expected trace distance when the rate is larger than the mutual information could be lower bounded by some exponential decay with the same exponent, but by some polynomial prefactor in front of the exponential. So we expect this kind of inequality holds, but right now we don't know how to prove it. But we conjecture that the error exponent we obtain is the best, is the optimal one, and there's no other exponent. We cannot have a larger error exponent. If I have time, I will explain why we think so later. Okay, so and also our result is strong enough to obtain what we call a moderate deviation asymptotics. The moderate deviation means that, so our previous result is a kind of large deviation result because it's like an exponential behavior, exponential convergence. If the rate is deviate from the mutual information by a constant amount, then we will have this exponential convergence. But what if our rate, this rate is also a parameter in n? For example, if it approaches the mutual information at some speed, an, where n is vanished but not too fast by a square root of n, we also obtain some result for this. Why do we want to consider this? Is because we want to sample as less as possible. And now we know that the mutual information is a fundamental limit, and we don't want to use too large rate. We just want to use a asymptotically the same rate as the mutual information. So we can use this moderate deviation sequence, and then our results show that the expected trace distance also vanish by some governed by some variance quantity. I will now introduce this, write down the explicit form for this, but we show that this expected trace distance will vanish when the rate approaching the mutual information at some speed, an satisfies this. On the other hand, if a rate approaching the mutual information from below at some speed, an, it will also approach 1. But this time, it's because this an square will vanish, so this is a sub-exponential convergence. So in this case, it's not an exponential it's not an exponential convergence. It's a sub-exponential convergence because our rate now approaching the fundamental limit. Let me use this figure to illustrate the phenomenon. Okay, so the x-axis is the rate of the code book R, and this is the fundamental limit of mutual information. The y-axis is the trace distance, epsilon. So if you use channel just once, and you can get something like this, something like that's the probably the best you can get. If you use the channel many times, you can get a sharper expected trace distance. And you use channel infinity many times, you'll get this sharp state function. For these two regions, we call the large deviation regimes. When if the rate is constant away from the mutual information, then the trace distance will converge to 0 exponentially fast. When the rate is too small, you converge to 1 exponentially fast. We call this large deviation regime. The moderate deviation regimes describe these two corners. If the rate converge to this x-axis, the rate converge to the mutual information at some speed, we call sub 1 over square root n, then the error will also converge to 0 or 1. From here is from above or from below. Okay. And this is in this work we derive those two results, the moderate deviation results and large deviation results. But we can also ask another question: if the error is constant, is fixed, then how fast the rate of those curves converge to the mutual information? And in our follow-up work, we show that the convergence is by 1 over square root n. Why is 1 over square root n? Because it follows some central limit theorem result. So we can use some central limit result to show this convergence. Okay, so that's our result. Let me give you some ideas to prove this exponential convergence. Okay, actually, our proof techniques is not very new. We follow some functional analysis techniques called complex interpolation theory, and there are already some book from a very old book, and also by Pisier, which he's a very good mathematician in non-commutative functional analysis, and also Kosaki. He studied many non-commutative LP spaces. We just use some techniques in the books to solve our problem. So what is complex interpolation? Let me give you some examples. So if we consider a classical LP space, and we can define the LP norm just by, I think you already know the LP norm for the classical measurable functions. Okay, in the matrix case or in the non-commutative case, we can define similar things. Oh, I forgot to mention that. And because LP space is an interpolation family, so you can upper bound this every p theta norm by some p0 norm and p1 norm if we call this Holder conjugate or Holder parameter or something like p theta is satisfy this relation. Then we can bound the every p theta norm by some boundaries. If you can control p0 norm and p1 norm, you can control the every p theta. So that's why we call this interpolation. Okay, so this holds in the classical LP space. You can view this as a kind of Holder's inequality or some kinds of literal Holder's inequalities. But for the matrices, you can also use this Shelton P norm defined by this, also in a very similar way. And it turns out that Shelton P class is also a complex interpolation family. So the matrix Holder inequality also holds, meaning that for operator A, the P theta Shelton norm can be upper bounded by those P0 and P1 Shelton norms. So that's the interpolation inequality. And we found that that's very useful in our analysis. Also, you can check the Batia's matrix analysis proofs to find those matrix Holder's inequality. And actually, it holds beyond matrix case. It also holds in the infinite dimension case. It holds for operators and also in von Neumann algebras. But I will not touch that in this talk. Okay, so let's look at our proof sketch. We will take a functional perspective from non-commutative L alpha space. I'll use alpha here because we use P for input distribution. So later I will just use this alpha, L alpha. Okay, so for any operator valued function from some sample space omega to the bounded operators, or this is the operator value function, we define this L alpha S alpha norm by this. We first take for each sample omega, and this is f of omega is an operator. We calculate the S alpha norm of this operator, just Shelton alpha norm because it's a matrix. And then we raise this norm to the alpha power and then we take integration with respect to the distribution for those omegas. And then we take 1 over alpha in the end. We call this the L alpha S alpha norm. S alpha is to calculate this operator. L alpha is a classical L alpha norm to calculate this norm. Okay, so we call this L alpha S alpha norm. It's well defined by Kosaki. Okay, and we will introduce some other operators for each small m. Small m is each our sample in the code book. We introduce this small pi m, which is an embedding from the original probability space to the m-fold probability space. It is because that we sample m times in the code book, so essentially they are the m-fold probability. They are m-fold probability. And we introduce this pi m by the embedding. We calculate each pi small n by just evaluate the function at the mth probability space. So it's an embedding. We also use some capital E to denote some constant valued function. It always output an ensemble averaging of this operator value function with respect to some probability input distribution P. Okay. Then we further define some linear operator big theta as this guy. We take a mixture of those small pi m and minus this constant value function. So at this point, you may already know that why we want to introduce this is because this guy acts as an empirical averaging, and this guy is always constant, and it's actually a ensemble averaging. Okay, so that's our notation. Now we'll go to our proof. So for every CQ channel with a random cost means that we take a sample and we have some X input in the codebook, and we send the codebook into the channel. So meaning that because each random code X omega is random, and the random is coming from these samples omega. Then the mapping from this small omega to the output to the density is an operator valued function, mapping from the sample space to the set of bounded operators. So this map is operator value function. So we can use the L alpha S alpha norm described before. So this is our expected trace. This is our objective function, the mixture of those density operators and the true marginal distributions. And each omega m in the m's probability space depends on small m. We'll take the expectation because the randomness comes from each probability space. And we use our notation, we can rewrite this whole thing in terms of an L1 S1 norm of this linear mixture operation on the operator value function. Let me mention this again. This map from omega, the sample space, to the density bounded operators is an operator valued function. So we take this linear operator on this operator value function. So because this f right now is an operator value function, so we take this linear operator, the linear mixture on this small f. This f is a composition of the random corpus and a CQ channel. So that's why we can write this in this form. So so essentially, our objective function can be written as an L1 S1 norm. So we just analyze this L1 S1 norm, and we are done. Okay, so our first step is to use the Holder's inequality to bound the L1 norm, because we can bound the L1 norm to some alpha norm, L alpha S alpha norm, and the L2 alpha prime S2 alpha prime norm, where alpha prime satisfies this Holder's relation. We can bound this, and sigma b is any density operators. Well, you can use anything, but just by Holder's inequality, you can have these upper bounds at the first step. And also, we choose sigma b as a density operator. So the density operator to the power 1 over 2 alpha prime, and this quantity will take the L2 alpha prime norm on this quantity. This quantity will become just 1, because we choose sigma b to be a density. So this quantity is just 1, and we have the first one left. And then because this sigma b, there's no randomness for this sigma b, just a fixed operator, we can put this inside in this linear operator. So we want to upper bound this alpha norm. If we can bound this alpha norm, then we are done. Okay, so now our target is to bound this norm, and I write out the alpha prime by this quantity. Okay, so let's see. It's a norm of a linear operator on some input. So we just use the definition of the operator norm to upper bound this guy. This is an input because it's from L alpha S alpha. So we directly evaluate the L alpha S alpha norm on the input, and this guy is the operator norm from the L alpha S alpha to the M4 L alpha S alpha norm. This is operator norm for this linear operator. So we split the contribution from inside, from input itself, and the action, the linear operators, into two parts, and it is a product. So we will bound these two terms separately to conclude the proof. Okay, so in here, there's a sigma b. We can choose this sigma b for free. So after optimizing the base sigma b, this quantity is actually the exponential to some factor times the sandwich Rényi information. So we are done for this part. This guy is just equal to this guy. If we can bound this green part, then we are done. So how to bound this operator norm for this linear action? So for alpha equals to 1 by some triangle inequalities, not so difficult, we can bound this quantity by 2 by using some triangle inequality. For alpha equal to 2, then we will consider L2 S2 space is actually a Hilbert space. We can use some. It's like a variance quantity, so we can use some pairwise independence of random code books. We can bound this the operator norm of this linear operator by 1 over square root m. This square root m comes from the variance of IID random variables. Okay, so these two are not actually, they are not difficult to obtain these two bounds at the alpha equal to 1 and alpha 2 equal to 2. Once you can control the boundaries, you can use the norm interpolation to bound every alpha between 1 and 2 by the norm interpolation, which by properly choosing some p theta, and then you can obtain this guy. And this constant does not matter, it's upper bounded by 2, I guess. And then this m up to this quantity combined with the sandwich Rényi divergence, then we are done. So you can also see why there's a trade-off between I alpha and also the size of m, because it's like a trade-off. Because like we want to take the minus of them then to see if the exponent is positive or not. So that's our proof strategy. Okay, let's go to some applications in 5 minutes. So our motivation is actually not math, it's about quantum information theory. We are considering a classical quantum wiretap channel. What is a classical wiretap channel? Let me introduce here. If we want to send some message small m through a classical quantum channel, we'll first do some encoding to map each small m message to some code book, to some symbol, code word, and we'll send it to the channel. We'll maps to the output Roby XM, and Bob will do some measurement to extract this m hat to get guess the same message. However, right now this channel is wiretapped because the output also has some can be access to some eavesdropper, because the output is Roby E and Bob only access the Hilbert space B, but Eve can access to the Hilbert space E. So the eavesdroppers can obtain this we call a quantum side information, and the Eve can do some any measurement he wants to guess the small m Alice sent. We call this the wiretap channel coding case. We want to design some encoding and decoding such that the eavesdroppers will have some negligible information of m. So that's our goal. So the secrecy criterion here is that we want that this rho E xm, this depends on this small m, is close to some density operator which is independent of small m, such that if cannot guess what is the message Alice sent. Okay, and because Alice will choose a uniform message, so we take a uniform of this trace distance. That's the secrecy criterion. We want this secrecy criterion. We want this error to be very small, such that if we'll have negligible knowledge of the information sent by Alice. Okay, so that's the setting of the classical quantum wiretap channel coding case. So how do we do? Actually, we use a very old method proposed by Weiner back in 1970 to for each small m Alice want to send, the message Alice want to send, we enlarge this m by some private randomness, small k. So our this codebook is enlarged by two-dimensional indices. And we choose this hx according to some probability distribution, px. And this k, what is this k? This k, Alice choose randomly. We call this a private randomness from a set 1 to capital K. So, but if does not know this private randomness, it's only by Alice. So at if site, at if's perspective, he will receive a mixture of those small k. Okay. So if you use this private randomness, then now the secrecy criterion is like this. Now you can see that this guy looks like a mixture, empirical mixture, and this guy is like a marginal state is like an ensemble averaging. So for each small m, the message Alice want to send, at the encoder we choose this, enlarge this private randomness and choose this codebook according to some probability distribution. Then in the long run, the expected trace distance at each side is just the problem of the soft coverage. And by our result, we directly get an exponential bound for Alice's secrecy error by our result. And we also show that the secrecy exponent is positive, meaning that this error can be controlled if and only if the private randomness used by Alice is larger than the mutual information between Alice and Eve. And I think that makes sense because if has zero mutual information between Alice, meaning that if it's independent of Alice, then we don't need to worry about that. But if this has strong mutual information between Alice, then we need more randomness to fool Eve. Okay, so that's our coding strategy. And by our soft covering result and matrix concentration, we can show this control of Eve's, we call the leakage information at Eve. Okay, and in the IID setting, this leakage information exponentially decays by this error exponent. So that's our a direct application of our result. So that's our motivation. We want to study this information theoretic task and then we find this norm interpolation techniques. So that's the flowchart of our work. Actually, our motivation comes from the private and secure communication in quantum information theory. We want to solve this private communication. But then we realize that it's tightly is related to the concentration with trace norm. In the classical case, it's concentration with respect to the total valuation distance. But in the quantum case, we are dealing with the trace norm. And then we use the compressed norm interpolation techniques to prove the concentration inequality. In the end, we can control the information leakage to the eavesdropper. So that's our whole idea. And actually, we realized this before, but I studied this problem back in 2019. We know how to do this, how to relate this problem to concentrations, but I couldn't generalize the classical proofs to the quantum scenario because it's just too difficult. But now and I realized, we can use this compressed norm interpolation to solve this concentration with respect to the trace norm. So that's our novelty. And also classical information theory, they don't know these techniques at all. So I think we think we are doing the right way because our approach makes everything very elegant and simple, and we can take the classical distribution and also the quantum operators at the same time in the same framework. So that's our contribution here. Okay, let me go to the conclusions. We obtain the one-shot achievability means that one-shot error exponent and the strong converse exponent for quantum soft covering. And actually, we do for different codebooks. And in this talk, I only focus on the ID codebooks. And our texts come from norm interpolation. And actually, there are some quantum information theory people use those norm interpolation techniques, and it's quite useful. And I want to mention that our result holds for infinite dimensional Hilbert space as well, because right now there's no dimension factor anywhere. And also the norm interpolation holds for infinite dimension space, probably also holds for von Neumann algebra, but it means that our techniques is quite general. And we believe that our error exponent result is the best. The exponent is optimal, but strong confidence exponent is not tight. But so that is the open problem. We couldn't solve the asymptotic tightness of the error exponent. And if we obtain the expected deviation bound, can we get a tight probability deviation bound? And as there's any other applications of our concentration inequalities. So this is our concentration inequalities. You may think this is kind of complicated because this guy is a convex conjugate function. But you can just take the weakened case by taking alpha equal to 2, and it becomes more simpler. So it means that essentially, it means this. If you write out the definition, you can obtain this. So this is like a 1 over square root m decays if this m is larger enough. So we are wondering if there is other applications of this concentration inequality. Okay, then I will stop here, and thanks for your attention. Yes.
The bound is
By triangle.
independent of n, right?
E
Less than 2.
Yeah.
Is this rough bound or is there any explanation for this?
For the alpha 1 case.
Alpha 1.
I actually don't know, but it turns out that just the one case does not.
Is the bound can be improved in some sense? Depend.
Probably, but you can improve it by some constant, but it only be a constant improvement. It does not affect the error exponent. So, yeah. Yes?
So, in a big data
Yeah.
setting, one advantage of concentration inequality is that it doesn't really depend on the dimension.
Yeah, exactly.
Where is the dimension here? Is it the dimension of x, or I lost track of the dimension of x?
X.
Is the dimension of
X.
So
And
this is
yeah,
independent of the dimension of x.
X. Actually, the dimension is hidden in the mutual information.
That's why I was asked, where is the dimension?
Hidden in here. If X and B have some strong correlations, then we know that the mutual information, this guy is upper bounded by the log of the dimension X and log of dimension B, the Hilbert space of B. If the mutual information, that's the worst case. So the dimension actually hidden in the mutual information. But in many scenarios, the mutual information can be strictly smaller than the dimension bound. So that's very interesting.
So I can mention that your method applies to infinite dimension.
Yes, yes.
But my question is, we have current channel when we deal with finite dimensional spaces. But how to get a current channel in the
Well, in some we call the Gaussian channel or some bosonic channel, there are some physical models that have infinite Hilbert space. Yeah, I agree. Like in quantum information theory, also we usually deal with the finite dimension case.
And is there any envelope problem for quantum channel?
Oh, fully quantum channel.
Because we can associate a quantum channel with a choice matrix.
Yes.
And we can approximate the choice matrix by your result here. So my question is there any...
Yeah, that's a good question. So if you take any state at the output as a choice state of another channel, yeah, that's a good question. I never thought about that. But I would say in this picture we have physical meaning, so we can sample.
There's no physical meaning that has.
Yeah. So.
Any other question or comment from the speaker? Okay, if not, let's send our speaker.
Thank you.